Voilà, alors je vous souhaite la bienvenue à l'UMH pour cette soirée assez exceptionnelle. Exceptionnelle à beaucoup de niveaux. La première, c'est une collaboration quand même assez importante entre l'UMH, les collègues de la Polytech et l'ASBL La Malogne. Exceptionnelle surtout parce que on a Monsieur Hoover qui nous a fait l'honneur de venir directement des États-Unis pour la conférence d'aujourd'hui et de demain. Donc ça, c'est assez fabuleux. Et donc Monsieur Hoover est un des plus grands spécialistes de la NASA dans le domaine des météorites. Alors, je vais laisser la parole à notre ami Jean-Marc Bail de la Polytech, qui est géologue, qui va vous présenter plus en détail M. Hoover. Welcome to Mons.
Okay. Merci.
Oui, bonsoir à tous. C'est un grand honneur donc de recevoir le professeur Hoover ici, qui est venu, comme Francesco l'a dit, spécialement des États-Unis, du Marshall Space Flight Center de Huntsville en Alabama, où Richard est on va dire le président, le leader du groupe de l'astrobiologie, donc cette science qui étudie la vie, les possibilités de vie extraterrestre, et notamment l'origine de la vie, les relations qu'il pourrait y avoir avec les origines de la vie ou l'origine de la vie sur Terre. Alors, bon, il a un curriculum vitae kilométrique, je vais évidemment pas vous le passer, mais je vais quand même citer quelques repères, puisque le professeur Hoover est auteur-éditeur de pas loin de 38 livres, de plus de 300 publications. Je vous passe les distinctions scientifiques. Alors, au niveau de sa recherche, donc, il est évidemment spécialisé en astrobiologie, mais plus particulièrement dans l'étude des bactéries fossiles, des bactéries qui vivent dans des habitats a priori que l'on pensait impossibles pour la vie. Donc il étudie ce qu'on appelle les extrémophiles. Il va nous montrer des extrémophiles, des bactéries qui vivent dans des températures très très grandes, dans des domaines de pression très très grands. Il a étudié beaucoup les biomarkers, donc les recherches de traces de vie, qu'elles soient actuelles ou anciennes, des biomarqueurs chimiques, des biomarqueurs morphologiques, aussi bien dans les météorites que dans des roches terrestres très très anciennes. Alors, c'est un scientifique de haut niveau, je vais dire, de laboratoire, vous l'avez deviné, mais pas seulement, et c'est ça qui est très important, c'est un scientifique de terrain, c'est un homme de terrain, il a fait énormément de terrain, il a parcouru la planète à la recherche d'environnements hostiles, comparables à celui de certaines planètes, et il revient juste de mission en Antarctique, mais il a été aussi en Alaska, en Sibérie du Nord même. Donc déjà la Sibérie, ça évoque pour nous quelque chose de très hostile, mais la Sibérie du Nord, je vous raconte pas. Dans les geysers de Californie, en Afrique du Sud, en Patagonie, en Grèce quand même aussi, à Hawaï, bref, partout dans le monde. Alors il a participé à la découverte, ou en tout cas découvert 2 nouveaux genres bactériens et 7 nouvelles espèces de bactéries et d'archées. Donc c'est pour vous dire que il augmente notre connaissance au niveau du monde des micro-organismes. Donc je vais lui laisser la parole. Ce soir, si je ne me trompe pas, parce qu'il y a 2 conférences, c'est les microfossiles dans les météorites. Et demain, ce sera un sujet beaucoup plus large lié aux origines de la vie, aux origines de la biosphère. Donc merci encore Richard pour être venu et je vous laisse la parole.
Thank you very much, Jean-Marc. I am delighted to be here with you this evening, and I had the opportunity to see the magnificent display of meteorites that you have here. It is truly wonderful, and it's very, very enjoyable for me to come and visit Belgium again, which I have to say I fell in love with when I first came here in the early 1970s, where I did the inventory of the Henri van Herk collection of diatoms in Antwerp. I'm talking tonight about microfossils of cyanobacteria in carbonaceous meteorites. As you know very well, the subject of microfossils in meteorites became very interesting and exciting in August of 1996 when David McKay and co-workers announced the detection of possible microfossils and an associated suite of chemical and mineral biomarkers in the Allen Hills 84001 meteorite from Mars. That observation associated with all of the biomarkers that they had found has ultimately been largely rejected by the scientific community due to 2 primary reasons. One, the structures such as we see here, the famous Mars worm. This is a 500 nanometer bar. They are so small that they cannot be definitively recognized by microbiologists or micropaleontologists as unambiguously biological. And the other problem, of course, is that they just don't have distinctive features, and they are in a size range that is extremely small. However, I must say there are some nanobacteria and dwarf bacteria that are not significantly different. So the size of at least that form is not disqualifying. But the problem is it is not possible to definitively say that these are biological. However, the McKay observation stimulated research in astrobiology, biomarkers in meteorites, and microbial extremophiles. The problem with attempts to detect and establish that one has found valid microfossils in meteorites is a profoundly important problem because it's directly relevant to the most fundamental question of astrobiology. Is life restricted to the planet Earth, or does life exist elsewhere in the cosmos? And therefore, in order to gain acceptance that you have actually found and shown the existence of extraterrestrial microfossils, you have to pass two very rigid criteria in order to achieve validity. The first criteria is biogenicity. Are the structures that you're finding really microfossils? Are they truly biological? Or can they be artifacts, coating artifacts, other kinds of mineral grains or crystals or other inorganic structures are the kind of things that Manuel Ruiz Garcia has been studying, which he calls biomimics. Well, in order to verify that you have valid microorganisms or microfossils, they have to be large enough to be autonomous organisms with sufficient chemical and morphological complexity so that they can be differentiated and distinguished from abiotic mineral crystals or coating artifacts. The other critical problem is indigeneity. Are they truly indigenous? Did they arrive on Earth with the meteorite, or are they forms that crawled into the meteorite rock matrix after the meteorite landed? That's the fundamental problem of contamination. And that is indeed a tremendously important problem, which I'll talk about more in detail later. It has been known for a long, long time that the carbonaceous meteorites contain a large suite of very, very complex chemical biomarkers. And in fact, these are the kind of chemical biomarkers that have been accepted by mineralogists and geologists for a long time as being valid indications of biology. And I'm not talking about weak biomarkers like the polycyclic aromatic hydrocarbons. I'm talking about very strong biomarkers like purines and pyrimidines, amino acids that exhibit chirality, in which you have a strong level rotary excess. That was first published by Engel and Nagy in Nature in 1982. It was disputed that these were probably contaminant amino acids. It's now known that they were not contaminants, that they are indigenous to the meteorite, and that they are truly amino acids with an L excess. On Earth, amino acids with an L excess are produced by biological processes, and there is no way that has ever been shown in which you can produce significant quantities of an L excess of amino acids by strictly abiotic mechanisms, such as polarized light from supernova remnants, formation on crystal lattice structures, and so forth. One of the fascinating things that Mike Engel has shown is that in the carbonaceous meteorites, Murchison and Orgueil, there are several amino acids like phenylalanine, tryptophan, lysine, histidine, arginine, and tyrosine that he does not find. These have never been detected in carbonaceous meteorites. Now that is profoundly important because biological entities contain this whole suite of 20 amino acids, and if they were biological contaminants from recent terrestrial materials, you should find all 20 amino acids in the meteorites. The missing amino acids, in my opinion, provide strong and convincing proof that these meteorites have not been contaminated by recent microorganisms. There are also phytane and pristane and norpristane, which are associated with the derivatives of the phytol chain of chlorophyll. No one knows how to abiotically make chlorophyll, and it's a profoundly important biogeochemical. So that is another piece of chemical biomarker evidence that biology has been associated with meteorites. When I first met academician Eric Galimov in Moscow several years ago, he was very skeptical about this idea, but as I showed him pictures, he says, you know, he says, the Murchison meteorite has always troubled me, and he did this wonderful book on biological fractionation of stable isotopes, and he did studies of thermodynamic isotopic fractionation, And in his book, he showed me this plate in which he showed that there was a very similar analogous relationship between these amino acids in Murchison and what you find in Euglena, in Gracilaria, and in Chlorella. I looked at this plate. I had never seen it before. I said to Academician Gallimov, this is one of the most solid pieces of evidence for the existence of microorganisms indigenous to the carbonaceous meteorites that I have ever seen. He said, well, he said, yes, I guess I can see how you could interpret it that way. He didn't interpret it that way because, of course, at that point in time when he wrote his book, the idea that microfossils or microorganisms might be associated with carbonaceous meteorites had become essentially taboo. The kind of work that I've been doing at NASA for the last decade, a little over a decade, I started this shortly after the McKay announcement. I use optical microscopes, such as the LIGHTS microscope, for looking at color and characteristics, which is a good way of differentiating between recent contaminants and valid indigenous materials. But basically, we've been using a suite of environmental and field emission scanning electron microscopes. As you see here, I won't go into great detail about the instruments. Since I started this study, I have investigated a large number of carbonaceous meteorites and non-carbonaceous meteorites. The most exciting are Orgueil, Ivuna, and Orgueil, and also the C2 ungrouped Tagish Lake meteorite, and then the CM2s, Murchison, Miguel, Murray, and Nagoya, and several other types of carbonaceous meteorites from various places around the world. I've also looked at stony meteorites like Nikolskaya and Barata, Holbrook, and diogenites like Tatooine, and iron meteorites. And in fact, we collected 20 meteorites in Antarctica during the Antarctica 2000 expedition. The ones that are shown in italics, I have found no evidence of microfossils whatsoever. The ones that are in non-italics, especially those in red, are where I found what I consider to be truly abundant assemblages of microfossils. As I said, contamination is profoundly important, and so I've taken great care to ensure that the samples are not contaminated. These include studying only in freshly fractured samples and only looking at the interior surfaces, being careful to avoid the fusion crust surface unless there's some particular reason that I'm wanting to study the fusion crust, but being aware of the fact that the fusion crust is a possible region for contamination. I use all new electron microscopy mount stubs and sterile tools. I do flame sterilization of all containers, stubs, and tools. And for long-term storage, I store everything at -80°C, or for short-term storage in desiccator cabinets. And I never use any contact with liquids or coat the samples. If I don't coat the samples, then I can't be accused of looking at coating artifacts. And the sample is placed in the field emission scanning electron microscope chamber right after it's fractured. Now, David McKay's announcement of evidence of possible microfossils in meteorites was not the first time people had found evidence of structures they considered microfossils. Way back in 1961, Bartholomew Nagy and George Klaus reported the discovery of a suite of structures that they considered to be biological in the Orgueil and the Ivuna meteorite. They were immediately criticized and challenged by Fritsch and Anders, and so they retreated. They said, we're really not sure if these are truly biological, but they have structures that are similar to biology. And so they started calling them organized elements, which said they have complex structure, but we don't know where they came from. In 1963, the famous Russian scientist Timofeyev reported finding acritarch-like forms, and these are some of Timofeyev's acritarchs. These are Klaus and Nagy's original images of what they considered to be microfossils or organized elements. One of the problems was that in their original paper, they had actually published a picture of a pollen grain, and that has led the scientific community, based primarily on a paper that was published by Ed Anders called Contaminated Meteorite, to come to the conclusion that all of the studies of microfossils in Orgueil were studies of pollen grains or studies of something that was put in intentionally as a hoax. They reported that they had found a hoax that had been carried out in the last century, in which someone had actually put in reed fragments and pollen grains and bits of coal. So in one single paper, they were able to explain all of the organics. They were able to explain the presence of kerogen in the meteorite. Somebody put coal in the meteorite. They were able to explain everything as strictly contamination. And that paper led to a complete demise of the study of microfossils in meteorites, and in fact it became essentially rejected and abandoned for research by the scientific community. The problem, of course, with the Clausen-Nagy form is that these small spherical forms, they were obviously indigenous, but they couldn't be ruled as being conclusively biological. Tan and Van Landingham found these kinds of forms, and they published those, and they had these little electron-dense solid bodies, which we now recognize as magnetosomes that are characteristic of magnetotactic bacteria. But in 1967, no one would have known that because the existence of magnetotactic bacteria was not known at that point in time. Their forms are clearly biological, but due to the way in which they did the cleaning and acid maceration, it is not possible to say that they are undeniably indigenous. Well, during my studies, I've had an opportunity to do a study of one very badly contaminated sample of the Murchison meteorite. It was sent to me by Meenakshi Vadva of the Field Museum. Here you see an environmental scanning electron microscope image, and here are 2D maps in oxygen, carbon, silicon, nitrogen, and iron. And you see these big, beautiful filaments here, and they trace very nicely in oxygen and carbon. But you also get these very nice traces of these filaments. You can see this form shaped here in nitrogen. When I started studying this particular material, I was very excited at first, and then some of the filaments started moving around under the beam of the electron microscope, and I became very suspicious, took it out of the microscope, and looked at it under my optical microscope, and I could see that it was a fungal contaminant because I had accidentally wandered off into an old crack in the surface of the meteorite, and I was looking at fungi that had been growing along the surface of the meteorite and had invaded this crack. Instead of throwing it away, I put it back in the microscope, and I did extensive studies to get a better idea of what does contamination look like when you actually find it on a carbonaceous meteorite. This is recent biology that had been growing on the Murchison meteorite sample from the Field Museum. Now I'm going to talk a fair bit about cyanobacteria. Not all of the forms that I find in the meteorite do I consider to be definitively cyanobacteria. And the problem is there are a lot of sulfur bacteria and other filamentous bacteria, such as the ones that Jean-Marc studies, that have very strong similarities to cyanobacteria. But I've investigated a whole host of living cyanobacteria, both in pure culture. This is a list of them. I won't go into all the details there. And in environmental cultures. And I have many different genera and species growing in my laboratory back in Huntsville. So anytime I want to look at living cyanobacteria, I simply put them on a stub and go over and stick them under the electron microscope. Working with Alexei Rozanov in Russia, I've had the opportunity to study fossil cyanobacterian phosphorites from the lower Cambrian Hessen stage, the Timothian stage from Hoover, Mongolia. Tufogenic rocks from the upper Archean, Lopian of northern Karelia, 2.8 billion-year-old rocks. And these were samples from Professor Rozanov. Briefly, cyanobacteria are very important organisms on Earth because they're oxygenic photosynthetic prokaryotes. They were originally called blue-green algae and studied by botanists. We now know that they're truly bacteria. They use water as the photoreductant and carbon dioxide as the source of carbon for their energy, and they release oxygen, and they were primarily responsible for the oxygenation of the atmosphere of the early Earth about 2.7 billion years ago. Some are facultative chemoheterotrophs and can use the photosystem II for anoxygenic photosynthesis of hydrogen sulfide. Cyanobacteria reproduce by a whole host of mechanisms, including fragmentation and the formation of hormogonia, by binary fission, multiple fission, formation of spores, aconites, and so forth. But the fascinating thing is that due to the fact that they mostly reproduce by binary fission, their size has remained unchanged, and people that have been studying cyanobacteria in the fossil form in very ancient rocks have been able to trace them back billions of years, and you can recognize analogs of modern genera and species in the very ancient rocks, and you usually called them, instead of oscillatoria, oscillatoreopsis, or Paleolingbia instead of Lingbia. You give the genus name a suffix or a prefix so that you can say, I'm talking about a morphotype of a cyanobacteria that I recognize. The morphology is important. They typically have a trichome that's a linear chain of cells, and it's most often found within an exterior envelope or a sheath. The sheath is typically a slimy, colloidal, non-cellular structure that envelops this group of cells lying in a chain. The trichome with the polysaccharide sheath is called a filament, and the filament can be polarized, in which case one end of the filament looks totally different than the other end of the filament. It can be uniseriate, where there's only one trichome within an envelope. It can be multiseriate, where you have many trichomes within a single common sheath. It can be branched or unbranched, and the branching can be true or false. It can be constricted, uniform diameter, or tapered. And all of these morphological characteristics are distinctive of different genera and species and orders of cyanobacteria. They also have very highly distinctive specialized cells for reproduction by Hormogonia and aconites, and very specialized cells for fixation of nitrogen in these structures called heterocysts. They typically have gliding motility, in which they slide along within the sheath, and after they leave the sheath frequently collapses and sometimes becomes twisted or coiled, leaving behind very distinctive looking sheaths. Here are some photographs of living Lingbia. This is Lingbia plectonema wolii, and this is like a stack of coins, a stack of euros, and here is the cell that has died, which we call the necridium, and that's the way in which these Hormogonia are formed. Here's a dead cell, and here's a dead cell, and this little chain in here is the reproductive structure of the Hormogonium. It's a bunch of cells that will ultimately come out of the end of this sheath, and here are 4 of these Hormogonia. You can see how they're beautifully identical, and then each one of these starts growing by simple cell division and forms an entirely new filament. That's the way this organism replicates, and it's been doing that for approximately 3 billion years. This shows the same Lingbia wolii. Here we're seeing it in the electron microscope image, and here we see a Hormogonia in the visible light image. This is one of the cells lying down on it flat, so you see it looks like a coin. And here in the electron microscope, you can barely get a hint of the differentiations where the cell boundaries have occurred. Again, here you can see the small lines where the cells are in this Hormogonium on the inside of in the electron microscope. Here is a dimple where I hit it with the electron beam, and this is the carbon, oxygen, nitrogen, phosphorus, sulfur, and silicon ratio. The nitrogen content of living bacteria and cyanobacteria varies quite a bit, but it's almost never lower than 2% and almost never higher than 14 or 15%. There are 5 orders of cyanobacteria, commonly accepted now: the non-filamentous, which are rods or spheres, the pseudofilamentous, the order Pluricapsales. These are cyanobacteria that build a tube, but they're not living in typical linear trichomes like you have in the order Oscillatoriales, where you have trichomic, non-heterocystous, isodiametric filaments. There's also the order Nosticales, which are isodiametric trichomes that do form heterocysts, and then the order Stignometales. Now, in the carbonaceous meteorites, I have found representatives of all 5 of these orders. The spherical forms are very common, but they're not definitive. They're not easy to look at and say, just by morphology, I know those are biological. But some of these others are very definitive, and I should say I found extremely rarely the Stignometales. They're almost non-represented, but I found a few cases. Now we see some examples. This is in the Murchison meteorite. We're looking at forms similar to the Cruacacales. This is in the Orgueil meteorite. This is Orgueil, and this is Orgueil. This is fossil Cruacacales from the Bitter Springs Formation of Australia. So this is an image by Schopf, clearly cyanobacterial, a visible light image, of course. And you can see how similar this is to the forms in the Orgueil meteorite. But again, and you can actually see this carbonaceous sheath on the outside of this round sphere from the Orgueil meteorite. So I look at this and I say this is a cyanobacterial or a spherical colloidal bacterial form. However, there are lots of ways you can make spheres, and I see lots of spheres in my studies of the lunar dust. So if people are perfectly within their rights to say, okay, I don't believe those are biological. I don't have a problem with that. I know it's difficult to say conclusively they are. But again, now we start seeing filaments. This is in Orgueil. Here's a filament that's embedded in the rock going the other way. This is like multiple filaments within a common sheath, typical of what we see in the cyanobacteria known as Microfossils thonoplastes. And here on the outside of it is another little cluster of these small spherical forms. They're not perfectly the same size. They have a size distribution similar to what you expect from colloidal bacteria. Again, this is a form that nobody is going to argue with me when I tell them that it's a colloidal bacteria or cyanobacteria, because you have a clear sheath that has pulled away. And this one is not a problem at all, because it's in a deep ice core at Vostok, Antarctica, from 3,550 meters. So no one would argue about the biogenicity of things found in the deep Vostok ice. This is from Yellowstone National Park. It has a very high iron content. It is clearly biological. We've got it growing in culture. We know it's a microorganism. And this is in the Murchison meteorite. And you can see where this outer shell, which has a higher carbon content than the inner infilling rock, has been broken away. I consider that to be a valid microfossil. Here we have representatives of the Plurocapsules in the Orgueil meteorite. These are extremely rare. I've only found these in one sample, and I've only found a few of these representatives. But Plurocapsules have irregular shaped cells that are typically polygonal, colloidal, and they live within pseudofilaments. So you actually have a sheath that's encasing a whole array of these kinds of cells. And the way in which they reproduce is by these forms that are called basocytes. You see a couple of them showing hairs protruding from the end. And the Plurocapsules often form elongated sausage-like structures, such as we see here, that are embedded in the rock here and embedded in the rock here and here. So I look at that and say, if I found that in a terrestrial rock and told someone that this was Plurocapsules, no one would have any problem at all with that identification. This is in the Murchison meteorite, and here we have living Microfossils thonoplastes. You can see here where the cells are located. These little faint lines here are delineating the cells that are basically short cylinders. If you look closely, you can see hints of delineations and multiple trichomes within a common sheath, as shown here. Now, that's actually just a part of this image. This is the entire image, and you see a structure here. Notice we're not talking about nanofossils. This is a 20-micron bar. This object is about 120 microns in size. Once I knew where it was, I could see it with the naked eye. It is jet black in color and looks like a tiny grain of salt. It's small, but still big enough to be seen with the unaided eye. And here you have a bunch of other complex filaments around this structure. And when I did a 2D X-ray map, you see here it is in carbon. We're seeing this region here in carbon showing very brightly, and this area up in here going off showing an enhancement of carbon, and down in here. In oxygen, this is the phyllosilicate cap. So you see this glowing very brightly in silicon and oxygen. In iron, the microfossil type form has very, very low iron compared to the rest of the mineral matrix. But note in nickel, here are some hot spots showing that this nickel image is not noise, it's a real image. But the nickel is almost uniform. So this body has essentially the same amount of nickel as all around it here as you find up in here, and the same is also true of sulfur. If this were a recent contaminant, a recent biological entity that crawled into the meteorite, the nickel map and the sulfur map should look like the iron map. But the fact that they show uniformity tells me that this is indigenous to the rock matrix. It's supposed to be there. It arrived with the meteorite. I showed this to Academician Ivanov, and he told me to show it to Academician Zavarzin. When he saw it, he immediately said it was Cyanobacteria. And then he described the various features. The trichome that has emerged, a hormogonia, as I showed you previously in living state. This is a hormogonia of a Nostochacean Cyanobacteria. Here you can see that the filament has broken. The hollow tube where the cells have come out is actually fractured, and you can see that it's hollow there. But up in here, it becomes flattened, and you can see individual cross-wall constrictions here, which make it possible to actually measure the size of the cells. And we see here evidence of cross-wall constrictions here. And here's another one that has actually come out and then gone off over there before it finally died and the fossilization process started. Norman Lazaroff did extensive studies of coiling hormogonia in the Nostochacean Cyanobacteria, and when he looked at this picture, he immediately pointed out these structures that I had never paid any attention to and identified them as coiling hormogonia, which he is one of the world's experts on. And here you see them. The coiling hormogonia spiral around, and the end of the filament sticks up in the center of the hole. And here you see one here with a little tail sticking out, another one here, another one here. So all around this filament, and here we see the cross-wall constrictions. This is just an enlargement of that previous region, an enlargement of it here as well, of the first part of it. All around this cyanobacteria, there are structures consistent with the reproductive structures of that particular type of cyanobacteria in close proximity to it. So we have not just a fossil, but an entire evidence of an entire nature of a series of reproductive processes that are consistent with what is known in the biology by the people who study cyanobacteria. Here I've taken a spot map from here and here of that region, and I want to point your attention to this region right here between carbon and oxygen. There is no detectable nitrogen peak. Again, carbon in the matrix is very low, and we see there is no detectable nitrogen between the carbon and the oxygen. So if we take the nitrogen to be less than 5,000 parts per million, 0.5% or less, if we assume it is 5,000 parts per million, we get carbon-nitrogen ratios of 83 for the hormogonia and 12 for the matrix. That's one of the things. The nitrogen content in the microfossils is always extremely low compared to modern biology. This is the Murchison meteorite. It fell in 1969, 10:59 a.m. And you see here a bunch of little round structures called chondrules. It's a CM2 carbonaceous meteorite. Over 100 kilograms were recovered. The magnetites, uranium-lead dating indicates an age of 4.56 billion years. So this is older than the planet Earth. The cosmic ray exposure age was 800,000 years, so it's thought that this was a structure standing up on the surface of a comet that was exposed in space for about 800,000 years and then broke off and entered the Earth's atmosphere and came in as a carbonaceous meteorite. There is extensive aqueous alteration by water on the parent body, hydrous phyllosilicates, clay minerals, serpentines. It's chemically primitive, and except for the volatiles, the elemental abundances are essentially the same as the solar photosphere. 2.5% by weight of carbon and 3 to 11% extraterrestrial water, much of it in water of hydration in the minerals. It has a large amount of insoluble organic matter that's similar to lignite, coal, or kerogen. Over 74 amino acids have been found in the meteorite, including rare amino acids like alpha amino isobutyric acid and so forth that are not commonly found in terrestrial biological systems. Also, it's missing these critical protein amino acids that I mentioned before. I've been studying a number of samples provided by Bill Birch at the University of Victoria Museum in Melbourne. He's been very gracious in allowing me some extremely pristine samples of Murchison that have not been disturbed since they were collected in 1969. One of the things, this is a big filamentous form similar to Microfossils in Murchison, and this was the first image that I took of it. And after it had been studied in the electron microscope for about 2 hours, it had changed its morphology to this. And apparently what is happening is the heating of the beam has caused it to dry out, and it's driven off hydrocarbons, and so it has gone through a change in structure. But living microorganisms, if you expose them to the kind of exposure I had given this one, they would have been destroyed long before that. This is from Cardiff. In fact, this was found when I was doing a demonstration, and I broke a piece of the meteorite and had a group of students standing around while someone else was operating the microscope, and we encountered this, and the people there immediately thought they were looking at a beautiful gram-positive bacteria. It turns out it is very, very similar to this form that we described from Mono Lake called Tyndalia californiensis. It has subpolar flagella, and you can see the flagellar material all up across the surface of this living bacteria. And I interpret all of these little lines here as being bacterial flagella that have clumped across the surface of that body. So it not only has the right shape and morphology, but it has indications of flagellar structures, such as we clearly see here. This is Cyanobacteria in Murchison. You can see individual cell boundaries of these 3 cells within the sheath. And here you have a tapered cell, and there is an apical structure here that is clearly different than the rest of the filament. This is a comparison of that one that I showed previously. We're looking primarily at this filament. It has several trichomes within a common sheath, and it ends up here in a rounded structure. This is a Siphonophecus from Hoover, Mongolia. This is a Cambrian form. It's broken here, but here we can see the ends of several of these cyanobacteria that are embedded in the rock. And you see how similar the morphology of this end structure is to here, and how similar the morphology of the filament is to this filament that we see here. Not only similarity in morphology, but also similarity in size. My favorite of all the carbonaceous chondrites is the Orgueil CI1 Carbonaceous Meteorite that fell at 8:13 p.m. in little villages of Orgueil, Noailles, Saint-Clair, Argent-Saint-Clair, in France on the 14th of May, 1864. There was a brilliant fireball that was white to dull red that was seen, and after the fireball appeared, there were thunderous explosions. Some of the villagers even thought there was an earthquake. In fact, some were so frightened they thought it was the end of the world. Shortly after that, a bunch of black stones started raining down all around the village, and the villagers collected them and very excitedly made contact with the leading scientists of the day. And I've had an opportunity to study samples given to me by Claude Perron and Martine Rossignol-Strick in Paris, and Émile Ladier at the Montauban Museum, and also Paul Sapira from the DuPont Meteorite Collection of the Planetary Studies Foundation. Oops, what happened? Did I do something here? No. How come it went very large? I don't know. Let's see if I back up and come back. Will it? Nope. Something's caused the screen to go very large. Do you have any idea what is? We've got an amplification factor here. Computers are doing strange things this evening. I am sorry. It's looking good. Oh, the screen appeared here. It's fine here, but nothing is. The picture is supposed to be smaller than that. I'll go ahead and talk while he's trying to fix the image here. I can't show you very well. Yes, here is Montauban and Orgueil and Saint-Clair, Bordeaux up here. This area in here is where there was an intense light and sound was seen. The area all around here is where the explosions were heard, and this way out here that goes out to Orléans and strange. It just went automatically by Patiente. Yeah. Okay, now. Okay, it's back to its normal self now. Good. Excellent. Excellent. Good. Ah, that's it. Oh. That's what happened. Well, let's go past that. That's the movie it's trying to show. Is what's happening. Yeah. And it may not be finding the movie. Okay. Now let's advance past that slide. Just go one down. I have a movie here I was hoping to show you, but unfortunately, it's this one may not have a PowerPoint capable of projecting it. Let's go to this one. Yeah. Okay. Yeah. Let me try backing up one. Yeah. Okay. Oh, can we start it from? Okay. Yeah. Sorry. Okay. Yeah. That's good. Yeah. That's okay. Okay. Let's move that slide to the back. Let's come down and just find it and delete it. That will. Okay. All right. Okay. Good. Good. All right. I don't know if that was the. Yeah. No. We're. Yeah. Yeah. We hadn't. Okay. I'll start here. This is a spectacular image of a suite of microfossils embedded in the Orgueil meteorite rock matrix. This is the rock, and here you see Cyanobacteria and other filamentous forms that may not necessarily be Cyanobacteria. They may be filamentous sulfur bacteria, but here is a whole assemblage of biological entities embedded in the meteorite rock matrix. And what is very exciting is when I do 2D X-ray maps, here is the 2D X-ray map in carbon, and you can see that there's a carbon enhancement up in this area and along in here. But most interestingly, if you look close, you see this little structure here, which has significantly more carbon than the form back here behind it that you almost can't see. It shows up very black in the silicon, and here we see that this little guy has a little more silicon. But notice the sulfur map. This thing has all of a sudden become visible because it has an enormous amount of sulfur, and this one is now negative compared to that image in sulfur. In iron, you see that these forms all have considerably less iron than the rock matrix, but in nitrogen we can only barely make out a hint of this portion of this one. Basically, the rock has the same amount of nitrogen as everything here, except for a slight enhancement right along there, and that's because this does have a little bit higher nitrogen than the rest of the rock matrix. But all of these other forms that are just as clearly biological have no more nitrogen than the rest of the meteorite. Now, looking at the one I just mentioned previously, I'm looking at this little guy in high magnification. You see that it comes around and it has a conical calyptra or cap at the end. That particular kind of calyptra is well known in Cyanobacteria. The sheath is flattened. You can see here it's squished and it is dimpled in. And here is the 2D, the spot data taken from a spot right in here. And atomic, we're seeing 46% carbon, 0 detectable nitrogen, 15% fluorine, 1.17% sodium. This is a very unusual thing. We have on a few occasions found fluorine in these forms, but it's almost never seen. But sulfur is 22% and magnesium is 8.5%. So it's like a carbonaceous sheath infilled with magnesium sulfate. This is living Lingvia wallii, and here is a flattened hollow sheath. Here is a flattened hollow sheath, or flattened sheath at least. I don't know if it's hollow, but it has the same kind of flattened characteristics that we typically see. And here is a thick surface around the filament consistent with the sheath, and an emergent trichome consistent with an emergent trichome. This is living. This is the Orgueil Carbonaceous Meteorite. And when we look at this particular form, it's very exciting to me. It's the only one I found like this. I'm doing the 2D X-ray spectra right here. I also have spectra on the trichome, but they're almost indistinguishable. And the reason that I find this so exciting is even though this form definitely looks biological and recognizable, look at the carbon content. It has 0.01 atomic carbon. Nothing living or recently living would be found with 0.01% atomic carbon and 37.5% sulfur and 45% oxygen, 15.4% magnesium. So this is a magnesium sulfate, but this kind of fossil would be totally destroyed if I dropped any kind of liquid on it, water or alcohol. It would immediately go away. And you never find a fossil like that on Earth, because any time it is exposed to water, it would be destroyed, and we've had a long time in which fossils can be exposed to water. This is living. This is Oscillatoria lude from the University of Texas collection, and the reason I show that is to show what a flattened sheath looks like, and you see they coil inward like this. The trichome has emerged from this side, and the sheath is what's left behind. Here is in the Orgueil meteorite. You have a spiral at the end of this sheath. Then it ends in an emergent trichome up here. I want to point out that this is a 50 micron bar. So from here to here, it's about 125 microns. So we're talking about truly big structures, things that any microbiologist would be proud of. In fact, many microbiologists don't like them because they're too big. This is living Microcolia stonoplastes from Ludmila Gerasimenko in Russia. This is forms that I interpret as analogs from the Orgueil meteorite. I'll go through a number of these. This is in Orgueil, like formidium. This is tremendously exciting area because we have the tapered filaments. We can see cross-wall constrictions in this very strange-looking thing. And down here is a form similar to an aconite, and a very wrinkled structure here. When I look at it in higher magnification, you can see this nice wrinkled structure and the aconite and these cells structures coming up and ending in funnel-shaped structures. Alexei Rozanov took one look at this and said that is Leosporidia, which is an acritarch that has been extinct on Earth for a very long period of time. They were quite abundant in the Ordovician, but acritarchs do not live on Earth today. So if one wants to attribute this to a recent biological contaminant, it has to be attributed to a fossil that crawled into the meteorite, and fossils are not very motile usually. But the fascinating thing is that the great Russian expert on the father of the study of acritarchs found forms in the Miguel CM2 carbonaceous meteorite that he was convinced were acritarchs. And even though I've had people argue, well, he had acritarchs all over his lab and he just got the meteorite contaminated, I feel that's a nonsense argument because I have diatoms all over my house, and if I am looking at a particular diatom slide of Miocene diatoms, if I see an Eocene diatom in there, I know it's a contaminant. If these had been contaminants, then Timofeyev would have never bothered to publish a paper about them because he would have been too embarrassed that he had contaminated his own slides, because he would have certainly recognized what he had contaminated them with. This is a set of data looking at this center region of this tip of a filament and looking at the carbonaceous sheath that you can actually see through. It's an electron transparent carbonaceous sheath. That is shown in X1, and that appears in black. So you see this area and notice this is 2 microns. So from here to here we're going about a micron, and that's the difference in the carbon content there and in red in the filament center. And yet when you look in the filament center, you see much higher amount of magnesium and sulfur. So that's telling me that this central portion of the filament is infilled with magnesium sulfate, and the outer region is a carbonaceous sheath. Again, very, very interesting form. These are tiny coiled structures that were identified by Rosemary Ripke, who is a world authority on cyanobacteria. She did the chapter in Prokaryota on cyanobacteria as Lophotrichus tufts of Fimbriae. Here is a form showing a ribularian type cyanobacteria with a heterocyst, which is the structure used for fixation of nitrogen. We see lots of areas in the meteorite where you get thick mats, very similar to what you find in terrestrial mats. You see here, this is a Bisprocta and Golubic modern lagoonal mat from Tikua Atoll. This is in the Orgueil Meteorite, and this is in living material. This is a mat similar to a Microcoleus mat in the meteorite. A form that I consider a spirulina mat, embedded in the rock matrix but coiling all around the surface. Again, forms like you see in spirulina mat. This is very exciting because here you have a completely hollow sheath, a very high carbon sheath, and this is twisted, which is, in my opinion, evidence of motility, and again, a flattened sheath where the cells have left. Here we're looking at this point on this filament, 9, and again, the point is the nitrogen content is not detectable, 0, which means it's less than 0.5%, carbon 8.9%, and the sulfur 34%. Up in this one, right at this point, the carbon is 55%, the oxygen 13%, magnesium 6%, and sulfur 17%. So significantly less magnesium and sulfur, and we may actually be going completely through the thin electron transparent sheath and picking up magnesium and sulfur from the underlying rock. But the important point is the carbon here is 55%, where it's vastly lower on most of the forms that we find. That's one end of the filament. Similar kinds of mat material. Here we see a very nice, either a cell or an aconite on the inside of this sheath. Here's the long filament. You see only one form here. I tend to think this is probably an aconite inside of the filament. Again, this is Orgueil. When I was with Rosemary Ripke, she saw this picture and said, "Oh, those are beautiful Lophotrichus tufts of Fimbriae." Well, I was quite embarrassed because at that time I had never heard of that and hadn't even thought to try to look. And she described in detail that these were known on Cyanobacteria. They are known on a wide variety of bacteria, typically as attachment structures. They're found on E. coli and a variety of other gram-positive bacteria. This is a 2-micron bar. This is an image, low magnification. When we go to 80,000x, we're seeing those coiled filaments. This is a 200 nanometer bar. So each of these little helical structures is about 20 nanometers in diameter. These are clearly biological, recognizable structures that are almost never, they're common on cyanobacteria, on the oscillatorian cyanobacteria, but they're almost never seen because they stick to the sheath. They're so difficult to see and to photograph. Here is a very rare example in which you can see the individual cells on the inside of the sheath. Usually you can't see through the sheath and pick up individual cells, but that's not solely true of these fossils in the meteorite. That's true of fossil cyanobacteria in general. It's very rare with electron microscopy to be able to see that kind of structure. Here we see them, a series of these forms coming right out of the rock matrix, and they're broken because they broke when I fractured the meteorite. One of the exciting things about the ribularian cyanobacteria, particularly in genera such as Ribularia and Calythrix, is they have to have specialized structures for the fixation of nitrogen. These cyanobacteria have the ability to take atmospheric nitrogen and convert it into nitrates and ammonia. So they make the nitrogen in a form that is utilizable by biological organisms. And they do that by using a nitrogenase enzyme, and the nitrogenase enzyme is destroyed by oxygen. So you got a problem. You got an organism that carries out photosynthesis and produces oxygen that wants to carry out a process that can't have any oxygen. So how do you solve the problem? Well, these kinds of cyanobacteria solve the problem by making a structure called a heterocyst that has a thick wall that is impervious to oxygen. The nitrogenase enzyme is on the inside of the heterocyst, and it produces the ammonia. And as the ammonia or the nitrates come out, they go up the filament. And as the cells utilize this, they get progressively smaller as you go up toward the top of the filament. So that gives rise to tapered filaments such as we see here. So these typically grow with the basal heterocyst attached to the mud of the sediment in which they're growing. So here in the meteorite we have the proper kind of attachment, the proper kind of basal heterocyst, the right configuration for a Calythrix. The problem was when I found it, I said, this is impossible because nothing's ever been described of genus Calythrix that's this small. Calythrix is typically significantly larger than this. Here we have embedded filaments here as well. Calythrix is usually about 10 microns in diameter, and I've got guys that are 2 microns. So, and I'd gone through all the books, Geitler and Desiccateri and so forth, and I was lamenting this fact to Anne St. Amand at Phycotech, and she says, oh, Calythrix can get that small. I said, no, no one's ever described it. She said, I know, but I've got some. Would you like them? So from the Little White River of Oregon, she had samples of Calythrix, and she sent them to me, not in living state. Unfortunately, she had done a terrible thing. She had killed all these bugs and fixed them, but even so, they were nicely preserved. And here you see a Calythrix from the Little White River. This is a 4-micron bar. This is a 5-micron bar. These guys are perfectly consistent in size and morphology and characteristics to the Calythrix here as what we see in the Orgueil meteorite. Again, the heterocyst, the tapered filament, and the apical hair. That's from Little White River. This shows a terminal heterocyst rather than a basal heterocyst. This is in the meteorite, and this is a living pure culture of Talipothrix distorta, which has terminal heterocysts instead of basal heterocysts. I have this growing in my laboratory. This is from the meteorite, and that one is in captivity, but it's dead. This is a cylindrospermum, and here's another representative of cylindrospermum with a terminal heterocyst. It comes around a huge long filament, goes into a nice coil up here. This is in the Orgueil meteorite. This is one of the most beautiful forms in the Orgueil meteorite, and I think it may be a Stigonometalis. If so, it's one of the only ones that I've ever found. You can see the branching coming out here with very thin filaments coming out here, and you can see that this sheath is electron transparent, and I've taken EDS data on these kinds of spots. Here at S, we see right here, and there's the carbon and the oxygen. The carbon here is 82%, the oxygen is 9%, so we have an oxygen to carbon ratio of 0.2, very similar to what you would expect with coal or kerogen. And again, notice right there where there should be a nitrogen peak, there's no evidence of any nitrogen at all. It's difficult for anyone to look at that and convince me that that is a mineral crystal, especially with this kind of chemical composition. I presume we may have some mineralogists here, and if anyone has some thoughts along those lines, I would appreciate it. Well, one of the problems is, if these are truly biological, the argument has been, well, maybe the nitrogen went away because the meteorite fell in 1864. So I said, okay, how can I find out how long it takes for nitrogen to be removed by diagenetic processes? And I was of the belief that it took a great period of time, but I had no data to prove it. So I had collected tissue and hair of woolly mammoths while I was in Siberia. This is a bit of tissue and hair from a woolly mammoth from a 32,000-year-old layer in the Kolyma lowlands of Siberia. I hit the tissue right in here. And the undercoat hair, the thinner undercoat hairs up in here. And this is actually one of the undercoat hairs. The nitrogen is 11.6% atomic. In the tissue, the nitrogen is about 4.5, 4.6%. But again, 73% carbon, 14% oxygen. This is 32,000-year-old biological material still having plenty of nitrogen. I plucked some hairs out of my dog, Sasha. She didn't mind. She thought I was grooming her. I was actually grabbing some hair to take in and put on the electron microscope. And this is one of her hairs that's clean. And you see the very definitive nitrogen peak here. We've got 72% carbon, 11.9% nitrogen, and 13.8% carbon. If I look at carbon-nitrogen ratios, these are filaments in the meteorite. These are living. Well, this is Bangia quadripunctata from 1816. This is Lingbia subtilis, and these are all cyanobacteria, modern cyanobacteria. Here, this one is an 11,000-year-old mammoth hair, 5,000-year-old pre-dynastic Egyptian mummies, 2,000-year-old mummies from Egypt, 1,000-year-old mummy from Atacama Desert, and Sasha's hair from 2007. So you can see modern biological and meteoritic microfossils. And here is carbon-sulfur ratios between the Orgueil filaments here. In this region are the Orgueil filaments, and they have very low carbon-sulfur ratios because they have enormous amounts of sulfur compared to modern biologicals from 1816 and on up, and then the 11,000-year-old mammoth, the 5,000-year-old mummy, and so forth. And you can see definitive, you would never confuse this portion of the graph with this portion of the graph. So in conclusion, I am convinced that there is strong evidence of indigeneity, that the fossils are embedded in the rock matrix. They have high carbon levels in many cases, and some are totally devoid of carbon. During the entire time I've done this study, I have never detected a single grain of pollen. The only time I have detected a biological material was this fungi from the Murchison meteorite, and that was the only sample that I found these fungi in. The Orgueil forms many of them are rare species, some of them with entirely unknown biological affinities. The EDS data shows that they have anomalous content of nitrogen and sulfur and cannot be interpreted as recent biological materials. So I have concluded that the Orgueil and the Murchison carbonaceous meteorites contain a large suite of recognizable microstructures, many of which are definitively recognizable as cyanobacteria, many of which are recognizable as biological entities. They could be filamentous sulfur bacteria or some other filamentous in-sheath bacteria. There is evidence of motility, evidence of replication, evidence of a whole suite of biological processes that are completely consistent with biology and not consistent with abiotic structures. There is also evidence of specialized cells like hormogonia and aconites and heterocysts. And replication, I found dividing cells, diplocoxy, chains of cells, aconites, cysts, spores, emergent trichomes, and hormogonia. And in fact, I found evidence of ecologically consistent communities in which I find several species that are recognizable, and then you find that those grow together and were described from cryoconite assemblages from Antarctica. In addition, we see very small structures like the Lophotrichus tufts of Fimbriae. So, in conclusion, I'm saying, without question, the Orgueil and the Murchison Carbonaceous meteorites and a variety of other carbonaceous meteorites, but not to that extent. Ivuna is also very nice. Ley is very nice, but I've had very little time to study those because the samples are so precious that I've had very, very small amounts of those materials. But they also contain evidence of microfossils. So my conclusion is that the carbonaceous meteorites, several of them, not all, the C5s, for example, Allende and so forth, I've not found any evidence of structures that I conclude are biological, but the CIs and the CMs largely contain evidence of microfossils that were present in the meteorite at the time it entered the atmosphere. I have no idea when they grew there, but I am saying I'm convinced that they did not grow after 1864 when the Orgueil meteorite entered the atmosphere. And I'm deeply indebted to a wide variety of people for electron microscopy support, for samples, and for extensive discussions that have made it possible for me to come to a lot of these conclusions that I would not have drawn if I hadn't had the opportunity to discuss these forms with many experts around the world. Thank you very much for your attention.
Si vous avez des questions, n'hésitez pas, on va faire circuler un micro dans l'assemblée. Qui se lance?
Au microscope électronique dans la météorite d'Orgueil, est-ce que vous devez chercher longtemps pour trouver ce que vous cherchez?
I think I understood the question. I believe he asked me how long did it take using the electron microscope to find fossils. Okay, excellent. Each sample is different, but I consider the fossil content of the Orgueil meteorite to be what I would call astonishingly rich. Sometimes I may have to look for 3 or 4 hours before I find interesting forms. Sometimes I put a piece of the meteorite under the microscope and I see these kinds of filaments within the first 10 or 15 minutes. I hunt other fossils, ammonites and trilobites and things like this. And if you go to a site and you find a nice trilobite or a nice ammonite, when you've been there 5 or 6 hours, you usually think you're doing pretty good. So, and if you hunt tarbosaurs or iguanodons, if you find one every few years, you're doing pretty good. So I consider the microfossils in the Orgueil meteorite to be astonishingly abundant, if they're prepared in the right kind of way. Now, if you take this meteorite and you do acid maceration, as many of the earlier workers did, you would destroy all of that. So the only way to really search properly is to just break the rock, put it on the stub, and stick it right in the microscope and start looking. It's that simple. You don't have to do any preparation. You don't have to do any hard work. You just break it and stick it in the electron microscope. But you really need an environmental or a field emission scanning electron microscope. Otherwise, you're going to get rather significant charging. If you want, you can do a light coating and still, because these are so large, you're really not going to be looking at coating artifacts. When you find these kinds of fossils, there's no possibility that you're looking at a coating artifact, even if you've coated with gold palladium or something such as that. Yes. Other questions?
Une autre question? Oui.
Merci. Moi, j'aimerais savoir, les cyanobactéries, à quelle vitesse elles peuvent se reproduire dans ce type de roche et dans les fossiles, enfin, dans les astéroïdes. Est-ce qu'une bactérie de ce type-là, ça se réplique vite? Est-ce que vous voyez par rapport à une...
I need the translation for that. Jean-Marc, could you tell me what the question was? Of growing. I am convinced that all of these things I'm looking at in the meteorite are dead and have been dead for a long, long time. But how rapidly did they grow when they were on the parent body? Well, I can't answer that because I don't really know what the parameters were on the parent body. I think what we're looking at, and if you come tomorrow night, you'll hear the same thing. I think we're looking at, in the Orgueil Meteorite, a piece of a comet. I think also that the Murchison Meteorite was probably a comet. I think that applies to the CIs, the CI1 group, and at least the CM2s. I think what we're looking at is, because of their water content primarily, are the remains of comets. Now, during the vast portion of the life of a comet, these biological entities, if they are on the comet, would remain in frozen state. And I study microorganisms in Antarctica, and when they're in frozen state, some organisms can actually live within the ice and produce enzymes that allow them to locally melt the ice. Some diatoms can swim along and grow and live within ice itself. But most organisms, when they get frozen, certainly when they get hard frozen, they go into a state of suspended animation. They do nothing. They wait until conditions get better. The ice melts, the permafrost thaws, and then in the springtime they can grow very rapidly. So replication rates of these kinds of cyanobacteria under ideal conditions could be divisions of once every half an hour, once every hour. Something like that, if the conditions were ideal. So you certainly once every half a day or a day. So within a period of a couple of months that the meteorite would have in its transit close to the sun and back around in regions where you could have sufficient solar heating to get liquid water underneath the crust of the comet, you could go through many, many generations. And if you have bacteria that are multiplying by cell division, it doesn't take too many replications before a small number of cells can produce an enormous number of cells. Yes.
Une autre question? Oui, Jean-Claude.
Peut-on évaluer l'âge de ces microbactéries fossiles?
No, absolutely not. All I can tell you is I believe they are ancient. I don't. By that I'm saying I think their age is in the tens of millions to billions of years, as opposed to the tens of thousands to hundreds of thousands of years. And the reason I say that is because I've looked at, for example, bacteria in deep Vostok deposits, and we see nitrogen in 100,000-year-old bacteria. So on Earth, in frozen state, ancient wood and ancient bacteria can remain with significant content of amino acids and proteins for 100,000 years. In fact, we have some living microorganisms that were collected by David Gilachinski and cultured by Elena Vorobyova from the Beacon Valley of Antarctica, and they were underneath a layer of volcanic ash that was Miocene. So these were older than the Miocene, and they are now growing in culture. So that leads me to believe that those microorganisms had been frozen for approximately 8.7 million years, and they were still alive. Well, if they were alive, they had all their protein, they had all their amino acids, they had all the structures that would have contained nitrogen. So that suggests that probably, since I see no nitrogen at all in the microfossils almost universally, there are a few that have 2%, but as a general rule, it's below the level of detectability. That aconite had 2%, for example, and that portion of the filament had about 1.5%, the one that I pointed out. But basically, the nitrogen has essentially gone away, and I think that means that these things probably grew on the parent body of the meteorite some tens of millions to billions of years ago. Now, I would dearly love to have someone where I could get access to a nanosims, where it would be possible to get in these tiny structures to get some stable isotope measurements and some other measurements that might help give a clue as to what the age is. But right now, sometimes people have had a tendency to say, well, since the meteorite is 4.6 billion, has magnetites that are 4.6 billion years, are you suggesting that the fossils are 4.6 billion years? Not at all. I'm suggesting they're younger than 4.6 billion years, but younger could mean anywhere from half a billion, 2 billion to 10 million. Anywhere in that range, I think. Yes. It's a big error bar.
Thank you.
Une autre question? Oui.
Do you have investigated the carbon isotopic ratio?
The carbon
Isotopic ratio.
No,
between,
no, we have not done carbon isotopes yet. I've been wanting to do that for a long time, but unfortunately, we don't have the ability to do the carbon isotope ratios. I talked with Brigitte Zanda in Paris. They do have the ability to make those measurements, but I haven't yet been able to make arrangements to come and do those measurements. Basically, since you're now trying to do a del 13C, for example, in a filament that's at most 10 microns or so in diameter, you've really got to have a nanosims type instrument. We can't do it with our standard secondary ion mass spectrometer. It's just not capable of working on samples that small.
Thank you.
Une autre question? Oui.
When you find purines or pyrimidines in a meteorite, can you still find chains of purine or pyrimidines in?
I'm sorry, I didn't understand. When I find
les acides nucléiques ou les acides aminés peuvent-ils encore être trouvés sous forme de chaînes dans les
it was
météorites?
better in English for me, but maybe I didn't hear it well. Can you tell me what he asked? Okay. Maybe say again. I just didn't understand what you said.
Amino acids or nucleic acids, are they still forming chains in meteorites, or are there just traces of purines or pyrimidines?
There are low levels of purines and pyrimidines. They have been detected, but they're not high levels of these materials. They're right at the level of detectability. The amino acids are present in very, very detectable levels. Some are, as I said, absolutely missing, but others are readily detectable by modern instruments that are available for that kind of studies. And it is absolutely certain that the amino acids are indigenous to the meteorite. They are extraterrestrial. Many of the amino acids found in the meteorite are not utilized in terrestrial biological systems, but others are utilized in terrestrial biological systems. Now, the fascinating thing I should point out, I failed to mention this, if you look at amino acids as Ostrom has done in hadrosaur, the same amino acids that are missing in the Orgueil meteorite are missing in hadrosaur bones. So ancient biological materials on Earth, and there's no one that's going to doubt that a hadrosaur bones or teeth is from a biological entity. When they're truly ancient, these more labile amino acids are destroyed and converted into other amino acids, so they vanish from the sample. So the absence of protein amino acids in the meteorite cannot be interpreted as proof that these forms are not biological. They could have had all 20 amino acids at some point in the distant past, and then the amino acids, that suite that is missing, have been converted into other amino acids or destroyed as a function of time. Did that answer the question?
But they never form a chain. They are not peptides. You can find traces of peptides in the sample.
Only traces. They're not extremely common, but of course the same is true of terrestrial fossils.
Une autre question? Oui, Pierre.
Donc, juste avant l'entrée dans l'atmosphère, tout était encore vivant alors. Donc la météorite, avant de rentrer dans l'atmosphère, tout était encore vivant. Non.
What's the question?
Just before entering the atmosphere or not? But there are microfossils.
Were the microorganisms in the meteorite alive just before it entered the atmosphere? I don't really think so. And the reason I don't think so is because of the nature of the preservation. I believe what we are looking at here, particularly where I showed those Lophotrichus tufts of fimbriae, I believe that what happened was the organisms were living, and then an explosion occurred, possibly as a result of pressure being built up under the crust of the comet and blowing out a chunk of material out into space, perhaps containing liquid water with the biological materials and mineral grains and so forth. And if you did that, the first thing that would happen is now it goes from a slightly pressurized container underneath the crust of the comet, or the water-bearing asteroid, whatever you want to think of it as. Claude Perron doesn't like the idea of comets associated with the carbonaceous meteorites. He likes to think of them as water-bearing asteroids. But my attitude is it's a distinction without a difference. Because if you have a water-bearing asteroid and it gets close enough to the sun to get hot, it would produce a tail, and an asteroid with a tail is called a comet. So I think what is happening is explosions occur, blowing out chunks of material containing the rock matrix of the cometary nucleus and containing ices and perhaps dead or even living biological material. And once it went out into space, the first thing that would happen is it would immediately vaporize, and you would have drying, as you do with critical point drying, by putting it in a good vacuum chamber, which deep space imitates very nicely. And the next thing that would happen is the temperature would rapidly plummet from whatever was being absorbed by the black crust of the comet and heating the interior to now the kind of temperature that you would get from rapid radiation into space. And so you would effectively freeze dry any kind of microorganisms that were there. And so even if they were biologically active at the time of the explosion, they would be freeze-dried. Now, if they were biologically active at the time of the release into space and they were freeze-dried, that gives rise to an interesting possibility. Because the best way to keep microorganisms alive for long periods of time is lyophilization. And in fact, all of the bacteria and archaea that we know of, we can store in a lyophilized condition. Now, the fascinating question is, if you think of this in terms of evolutionary biology, Darwinian ideas about evolution and modern biological evolution ideas, the problem is, how does something adapt to parameters it can never see? We say nature abhors a vacuum. That's totally untrue. Nature loves a vacuum. Most of the entire universe is a very good vacuum. But vacuums are very rare on Earth. In fact, you have to make them in the laboratory in order to get one. So only since Torricelli invented the vacuum chamber have we had vacuums on Earth. But bacteria have been around and living and growing and evolving on Earth for 3.8, perhaps 4 billion years. So where did they evolve the ability to sustain life after being exposed to liquid nitrogen temperatures and extremely hard vacuum? If they originated on the planet Earth. If, in fact, they were descendants of microorganisms that actually grew on a comet, then one can see a very easy way in which they could have adapted to this kind of what we have to consider are truly harsh conditions, because only in space do you find these kinds of hard vacuum and very low temperatures, unless you go into a laboratory and produce it yourself. So the answer is, I don't know, but I can still give an answer. Hope that helped. Well,
Une autre question?
Let me see if I can get my movie to play. That might be interesting here. Oops.
je peux aller. So, I'd like to pose another question. If you had a wish free for a new meteorite to come down to Earth, what would you hope to find?
If I had to wish for a meteorite to come to Earth, I particularly like I particularly like the CI carbonaceous meteorites. To me, the Orgueil and LA are the most spectacular. I should tell you what you're looking at here. I have just dropped a drop of water on a tiny piece of the Orgueil meteorite. And here it is under the microscope, and you're seeing in real time what happens to this meteorite when it is exposed to water. And if you'll notice, profuse array of bubbles are coming off of the meteorite. And here a piece starts coming loose. I'm moving around to look at other areas and coming back. I mean, it's just like champagne. And as you can see, bits and pieces of it are coming apart while it is simply exposed to water. Now, the reason that is happening is this meteorite is a microregolith breccia made up of billions and billions of tiny particles that have been cemented together by water-soluble salts. And that is the basic reason why we see these kinds of, there's the water dropping on it, and it immediately starts forming bubbles and breaking into pieces. I got distracted. I hope I answered your question.
And my question was if you are somehow waiting for a missing link to foster your research, if you're waiting for some new meteorite to come down.
If you're waiting for a new meteorite, actually the ideal thing to do would be to go and collect a piece of a meteorite. To go and collect a piece of a comet would be the ideal situation. And in fact, the Russians are planning an expedition to send a spacecraft to collect samples of Phobos that academician Galimov is directing, and to be able to study small chunks of Phobos returned to Earth would be a tremendously exciting thing, because it looks like Phobos may be a captured comet or carbonaceous chondrite type body. It has an albedo of 0.03, which is consistent with the carbonaceous meteorites. So the ideal thing would be to actually have a piece of a comet or a meteorite taken in situ in space and brought back. Then you would have the most perfect of all samples. Otherwise, a carbonaceous chondrite going through my roof and landing on my bed would be kind of nice as long as I'm not there.
Une autre question, Jean-Claude? Oui.
À ce sujet, par rapport à votre quête d'une telle météorite ou morceau de comète, ce que l'on a ramené récemment, et vous m'excuserez, je ne sais plus exactement sur quel corps céleste, mais il y a eu une sonde qui a permis de ramener certains fragments de je ne sais plus très bien quoi. Oui, Stardust. Si c'est cela. Est-ce que vous avez eu l'occasion, est-ce qu'on vous permet de pouvoir aller analyser de la même façon ces matières?
Okay. Problem is my brain starts working in English and I can't think in French. Can you translate again?
Could you repeat the question? It's too long for me.
It's too long. Okay. Oops. Okay, you have good. Maybe you'll repeat the question. This would be better anyhow. Good, and I will.
Voilà. Tu peux répéter?
Okay, I've got it. This is yes. I hear you wonderfully. Thank you.
Les matières qui sont revenues de Stardust ont-elles permis de faire, vous ont-elles permis de faire de telles recherches?
Excellent. Now I understand what you're asking. The stardust samples that were returned by NASA, very precious. There is a limited number of investigators that have been studying the stardust material, and I was not a part of the proposal to obtain stardust samples. So I've seen some of the results from some of the researchers that have been working on them, but I have not personally had an opportunity to work with any of the stardust material. I'd like to.
And what about the material collected on the moon, please?
The material collected on the moon. I have done a fair bit of work with lunar dust, with Apollo 11, Apollo 12, and Apollo 17 lunar dust samples. And I've got lots of photographs of the lunar dust on my computer here. There are absolutely nothing that I've seen in any of the lunar dust materials that I would conclude was biological in origin. There are lots of spheres and some double spheres that look like diplocoxy, and if you were to be looking at a sample from a lake, you would be tempted to say, okay, these are Crococcus or some kind of spherical cyanobacteria or bacteria. If you looked at the elemental analysis, you would immediately say, no, this is not possibly bacterial. Although there's some of them that are very high in carbon content. I've seen as high as 80% carbon in some of the lunar spheres. But none of the lunar dust that I've studied has any biological material in it at all. But there is a fascinating problem. All of the lunar dust samples that were brought back from all of the Apollo missions did contain amino acids. And they have never explained the origin of the amino acids in the lunar dust. It was originally thought that, we went to the moon and we made a big mistake and we contaminated the samples. Then they hypothesized that the amino acids came from the exhaust of the hydrazine fuel in the lunar lander. And so on Apollo 15, they had Jim Irwin go out on a rover a long distance away from the lander and shove over a rock, and they took a sample of soil from right under the rock, and they took a sample of soil from right under the lunar lander. And the idea was that when they got it back, the regolith from under the lander was going to have a lot of amino acids, and the regolith from under the rock wasn't going to have any, and they would know what the source of the contamination was. The problem is when they did the analysis, the regolith under the rock had a lot of amino acids, and there were amino acids but a lower concentration under the lander engine. So at that point, everybody decided, well, this isn't very interesting anyhow, and the study of it stopped. I think it was tremendously interesting, and I think it's a great shame that no one ever resolved the problem of where the amino acids on the moon have been coming from.
Moi, j'ai une question. Est-ce qu'il y a un consensus sur l'origine est-ce qu'il y a un consensus sur l'origine extraterrestre de ces fossiles de bactéries, ou bien c'est la bagarre entre spécialistes?
The extraterrestrial origin of
des fossiles de bactéries qu'on trouve dans les météorites.
I understand. The question was, is there a consensus about the forms that I am interpreting as microfossils? Absolutely not. Absolutely not. If you talk to the vast majority of meteoriticists, they will say this is total nonsense. There cannot be microfossils in meteorites. We know that. Why should we bother to look? And if you find the scientists, which are very common, that tell you that there cannot be microfossils in carbonaceous meteorites, the question I usually ask them is, how much time have you actually spent with a sample of Murchison or Orgueil with an electron microscope actively searching for these kinds of structures? And in fact, what you really need to do is, if the person is a meteoriticist, you need to find out if they first have spent any time actually looking at microorganisms under the microscope. Because microbiology, and particularly recognizing microorganisms by morphology, is a very specialized area. Jean-Marc can tell you that. He does that all the time. It takes time and experience to be able to distinguish between fossil bacteria and artifacts and mineral crystals and so forth. And you have to spend a fair bit of time learning what these kinds of things look like under the electron microscope in order to recognize what you're seeing. In fact, I've had people who study cyanobacteria express incredible shock when they saw their own cyanobacteria under the environmental or field emission scanning electron microscope, because they look different, totally different than what they're used to seeing. So you really have to develop a mental database and a photographic database by actually examining filamentous biology, examining living cyanobacteria and living sulfur bacteria and so forth under the electron microscope to develop an understanding of what you can see and what you can't see, and what it means when you see this and what it means when you don't see another particular thing. And then at that point in time, you're adequately prepared to go in and search the meteorite. But without that kind of database, or without actually working with someone that has worked on microfossils and living biology with an electron microscope, you would probably be able to have people who would look at the microscope and say, no, I don't see anything here. And in point of fact, they would be telling you the truth, because they wouldn't be recognizing anything. It's a matter of recognition, which requires developing a basis of knowledge that I have to admit, when I started looking a decade ago, I knew far less about cyanobacteria than I know now as a result of spending 10 years reading everything I can find about the subject. And that's the problem. It does take some degree of work, but I'm sure we have in the audience people who have worked with cyanobacteria and people who have worked with sulfur bacteria and fossil bacteria that know the difference in what they're seeing, and mineralogists and geologists that know that these kinds of forms cannot be simply dismissed as mineral grains or geological formations. They have distinctive sizes. That's one of the characteristics that differentiates biology from mineralogy. You can have quartz crystals, for example, that go from extremely tiny things to gigantic things. If you have, for example, a particular species of Spirocheta, or Spirocheta americana, its diameter varies from 0.2 microns to 0.24 microns. So there you have extremely precise size ranges, and if you found one of these organisms and it had a diameter of 0.4 microns, you can forget about it being that species. It simply cannot be, because it's outside of the size range. So size, size distribution, morphology, and chemistry are all very, very important parameters that play a significant role in all of this. And what I'm saying is that the size and morphology of the forms that I'm finding are telling me without a shadow of a doubt they're biological entities, and many of them are cyanobacteria. But their chemistry is telling me without a shadow of a doubt they didn't crawl into that meteorite after 1864 or after 1969, which says they were there when the meteorite entered the Earth's atmosphere, and therefore they are representatives of extraterrestrial biological systems. Not to make any bold statements,
Thanks.
but
Ok. Une dernière question peut-être, on arrête là, Lionel.
Have you an idea of what can be the genesis of such bacteria?
I'm sorry, I had my ears covered. Say again, please.
Have you ideas of what can be the genesis of bacteria?
What can be the
genesis? How they appeared?
The genesis?
Yes.
Where did they come from?
Yeah.
I don't know. But I have a number of ideas. I have to tell you, even though I'm saying that these are extraterrestrial biological entities, they may have come from Earth. And the reason I say that is the following. we've had many events where gigantic impacts have happened and ejected large quantities of terrestrial material into space. Now, if a comet or asteroid hits into the event forming the Chicxulub crater or any of these other giant craters and ejects terrestrial material, soil and mud and rock into space, it carries with it large amounts of Earth biology, much of which is going to be killed on impact. But not necessarily all of it will be killed on impact. So we could be continually seeding space with terrestrial biology. And in fact, that biology, if it remained alive through the ejection process, the first thing that's going to happen is it's going to go into a very cold kind of situation, become frozen, perhaps become freeze-dried, and now you're in an ideal condition for remaining viable until you happen to get picked up by one of the wanderers, for example, a comet sweeping through this debris field, picking up chunks of rock or ice or frozen mud that contains cyanobacteria, could provide an environment where these organisms could perhaps start growing. So maybe they're from Earth, maybe they're from Mars, maybe they're from Europa or Enceladus, or alternatively, if this happens in this way, there is nothing to prevent biology that was traveling around on a comet that got picked up earlier on Earth or earlier on some other system in the solar system from coming back through the atmosphere and landing in lakes or rivers or streams or oceans and starting to grow again. Because one of the things that should be noted, everybody thinks that meteorites get hot when they come through the atmosphere. That is true of nickel-iron meteorites, and it's true of stony chondrites, but it's not true of carbonaceous chondrites. Carbonaceous chondrites are also miraculous in that they're very much built like a returning Apollo command module. The outer regime of the carbonaceous chondrite gets very hot, and you see a fireball like was seen in Murchison and Orgueil. And as it is hot and coming through the atmosphere, you have an ablational process in which the volatiles and the kerogen and the organics are being heated to the point that they're vaporizing and they're streaming away from the meteorite, and you're getting a thin, hot fusion crust form, but most of the heat is being carried away just like it's carried away by the heat shield of a returning shuttle. So the inside of the carbonaceous chondrite stays cold. And in fact, we know that when meteorites have landed, one came through a barn in Noik, and a farmer in 1864 saw this black rock. It landed on a bit of hay. He apparently shouted, "Sacre bleu, qu'est-ce que c'est?" and reached over and picked it up, and it burned his hands because it was hot. But the hay didn't start burning, so it was not hot enough to set the hay on fire. Another piece, Madame de la Pulleroque found a piece in her garden on the morning after the meteorite fell, and May 14th in southern France, and it was covered with frost. Now, on May 14th, 1864, in the south of France, it was not cold enough to freeze water on the surface of this meteorite unless the meteorite contained ices after it had arrived on the surface of the Earth. So the hot crust was thin and very hot, and it had been cooled by passage through the atmosphere, and so it continued to cool down the very cold, large volume of the interior of this meteorite that was about like a grapefruit, began getting warmer, and the crust began getting colder until the crust got cold enough that water from the atmosphere condensed and then froze into a layer of frost on the outside of the meteorite. And the same thing happened to a meteorite in Murchison. So we know that carbonaceous chondrites, when they arrive, many of them are of the right volume ratio, that the interior stays frozen all the way through the atmosphere, and that means if there were any living biological materials on the inside of these and they landed in a pond or river or ocean, they might find they had encountered a perfectly happy home. And that may be the reason that one of the criticisms of what I'm doing is these cannot be extraterrestrial because they look just like many genera and species of cyanobacteria. So how could they have possibly grown somewhere off the planet Earth, since they are so recognizable with known terrestrial biological systems? Well, the point is, if this phenomena that I've just described is what is going on, those terrestrial biological systems may have originated on Mars or on a comet or on Enceladus or some other body within the solar system and entered the Earth's atmosphere 2.5 billion years ago and given rise to the grand explosion of cyanobacteria. Or they could have left the Earth 10 million years ago, hitchhiked on a parent body of the meteorite, and then come back in and we find them now. So that's a complicated answer to say. I really don't know, but I think the possibilities are very large that systems within our own solar system have been exchanging biological material for a long period of time.
Ok, merci beaucoup. Je pense qu'on va arrêter ici la séance de questions. C'est à mon avis une des conférences les plus animées qu'on ait jamais eues, parce qu'en général on a quelques minutes et puis ça s'arrête. Donc là on va arrêter parce qu'on doit raccompagner Madame Uchumaya chez elle. Donc avant toute chose, avant de remercier encore une fois notre conférencier, je tiens à vous rappeler que donc demain la thématique continue avec une conférence de Monsieur Hoover sur les liens entre comètes, météorites et apparition de la vie sur Terre. Donc n'hésitez pas à en parler autour de vous. Alors merci à Alain de la technique qui nous a sérieusement aidés. Merci à Madame Uchumaya pour la traduction, qui est un fameux exercice. Et merci à tous ceux qui ont rendu tout ça possible et à Jean-Marc de nous avoir amené Monsieur Hoover, et merci beaucoup à tout le monde. Voilà, alors l'exposition, elle est visible pour l'instant. Il y a des dates qui sont prévues pour les visites. Il suffit que vous alliez sur notre site web, soit olympus.umh.c.be, soit le site du Carré des Sciences, et ou alors vous tapez dans Google Météorites Mons, et vous tombez automatiquement sur la page qui reprend toutes les dates. On a quelques petits fragments de la météorite d'Orgueil, donc vous pourrez voir ça aussi chez nous. Voilà, bonne soirée, faites de beaux rêves et à demain. À bientôt.
Thank you.
Thanks.
Thank you.